Let me say a few words before I get started. That it's a real, first of all, thanks to the organizers for inviting me, and thanks to them for organizing this. And it's a real pleasure to be able to speak at something organized in honor of Mark's 60th birthday. I'll point out that Mark came to my 60th birthday, and this is going to be my turn for revenge and do exactly what he did, which is say only nice things. So Mark has had a long and distinguished career, and I'll first point out that he's managed to sort of do a number of things that I've done right after, which is really good because he did a much better job. So like various editor and the president of the Society for Math Bio, etc. And also somehow amazingly, after all these years, we've never written a paper together, which I think has probably been good because he's been able to, I'm sure, write reviews and write letters, etc. So that's been a good thing. But let me get started. This is going to be kind of a change of pace in the sense that I'm going to talk about two areas where I've used ideas, in one case very directly, in another case maybe a little bit less directly, but certainly played a very big role, ideas that Mark developed. And one of the things that's interesting is that this will emphasize that not only has Mark done great work, but he's done it over a very long period, because the first thing is going to be quite old. And secondly is that he's got great taste in the sense that the results are ones that were developed much more without a particular application in mind necessarily, and yet seem to say a lot about particular applications that are important. So the first is about systems of marine organisms with planktonic larvae. So think about organisms which live along a coast, and we always think of the Pacific coast, which you can think of as a straight line, the Pacific coast of the US, or Chile, works even better there. And these are organisms where the adults basically don't move much, ground fish, Dungeness crab, but then the larvae go out in the ocean and get spread around and move great distances. And so it turned out that Mark had written this paper long, long ago, I don't know if in 1997. He must have been, well, we won't, very young. And this turned out to be very, very important. And basically, they looked at this equation, equation 1 from their paper, which says that the number of individuals at location X next year is given by the production at Y times the probability of moving from Y to X. And since it's a math paper, there's some domain that's not necessarily specified as even being of a particular dimension or anything. And this turned out to be the absolute key for this paper, which looked at the configuration of marine reserves and how that would be their efficacy in maintaining the persistence of organisms would be dependent on how they're set up in a spatial network. And at the end, I'll point out, so personal communication, that this really has had a big impact. And so it's really traces back to Mark's paper. So what we did is, and this was work, as you saw, with Lou Botsford and Steve Gaines, is we set up a coastline. Think of this maybe as the ocean, and this is land, reserves, area, fished area, reserved area, fished area. And we talked about advection, but didn't do it in that paper, just diffusion. And we have a spacing. We assume they're equally spaced. And it turns out that, so one non-dimensional parameter is W over S. At that point, at least, there was this discussion, can you use non-dimensional parameters in an ecological paper or not? And we said yes. Though you'll see in a minute, when I write down the equations, they're not the ones from the original paper, because though the graph was done in a non-dimensional fashion, we didn't put the non-dimensional equations in the paper for some reason. And so it turns out we have a second non-dimensional parameter. And basically, if we assume that a dispersal kernel, and I don't know why we chose P, but we probably did for some reason, the standard double Laplacian, you get a mean dispersal distance, and then your second non-dimensional parameter, which makes a lot of sense, is the reserve width scaled relative to the dispersal of the species, so AW, which is then non-dimensional as well. And this is the equation that is the non-dimensional version then that points out. I'm not going to give you any of the derivation. And there's two pieces to this. And the first piece is the piece, well, let me do the second piece. The second piece, after the plus sign, is the contribution from a single reserve that gives you the approximate or number of organisms settling at the edge of the reserve. This comes out of this dispersal approximation that was the key clever part of the original paper by Kirk and Lewis. The first one was we then summed this up and basically geometric series, and you can again get the network contribution. And the claim would be that this has to be greater than some fraction, which is the fraction of the recruitment that would have been there if there was no fishing whatsoever. And this is some magical figure that you assume, and we took about 0.35 as the right number, and that plays an interesting role in what follows. And if you look as a check in the limit as W goes to 0, this reduces to M greater than gamma. What that says is that if you essentially have reduced fishing to a particular level across the whole system, basically you get back just that fraction back. So it's essentially, you've set aside then the that much away. And then this is the graph that was done non-dimensional, even though they were not. By writing in non-dimensional fashion, I'm not going to do it today. You can point out, and it's a little easier just to point this out. This says that you can get persistence because this is the 0.35. The flat curve is the 0.35. Focus on the upper curve. That's the one I was just talking about. If the width of the reserve is big enough, in this case, because we've chosen 0.35, it turns out to be 1. But if it's big enough, you get persistence. And the other way is if you essentially just have arbitrarily narrow reserves, you have to have this side be 0.35. And it turns out that there really is no network benefit in some sense, in the sense that you get one condition or the other, but you don't get any real benefit from having more than one reserve until you have a whole bunch, basically enough so it's the 0.35. And that you can only demonstrate, and was not in the original paper for some reason, only demonstrate by looking at the non-dimensional equation. Now, I'll point out that this paper turned out to play a role in the design of the marine protected areas that were put in off the coast of California, because it made a particular interesting simple point, which is that, think about it, is that if you have a very wide dispersing species, and that's basically can be determined by how far off the coast the larvae go, and so that candidate turns out to be Dungeness crab, that if you protect that species, you've protected every other species in the system that does have sedentary adults. And so as long as you design your network to do that, and that basic principle in a very crude sense was used to justify the design that was eventually chosen. So shifting gears, this is the second paper, and interestingly, we've just heard from Ping-Tuan and Mark, and this is for spreading speeds and linear determinacy for two-species competition models. And one of the areas I spent quite a bit of time over a long time doing, which may have led to the question I asked this morning, is a roughly 20-year project working with a wonderful former postdoc who we continue to work long after Brett Melbourne. And basically, what this whole project did was to look at primarily at an experimental system that looked at flower beetles and the laboratory, but relatively highly replicated, at least by ecological standards, not by other disciplines. And this is our attempt to look at two species systems. And a paper by Jeff Legault was the first author, and I kept hesitating because I wanted to get to the picture, is that typically we had this system with little boxes, think of them as about 2 inches squares, with little holes on the side that you can cover up with acetates. Early on, the old overheads that you used to use to give talks were very useful. After those finally got destroyed, had to buy some new things. And well, there's a system held together by rubber bands, so we can open up the holes. We make it into a discrete time. The population is discrete time, discrete space. You can essentially destructively sample. You put the adults in, you let them lay eggs for a certain amount of time. You take them out with a sieve. You put what's back. You wait appropriately, essentially 1 generation time. You count the emerging adults, and you keep doing it. So you have complete data, as accurate as the undergraduates who are paid to do the counting is. This was an experiment done in Colorado. I think we had better ones for the ones that were done in Davis. And this is an example of what we could do. And this is one of the species, Tribolium castaneum. And this is the example with no competition, and this is the mean abundances over a number of replicates. And this is generation 1. The colors represent different generations, and we ran this experiment for 8 generations. And this is actually a huge amount of work to do. And then this is the same kind of experiment with competition, and this is kind of visually showing you the result, which corresponds to the kind of result that was obtained in the paper I mentioned, Mark, to demonstrate that, which is you see the change. Oh, there it is. The change in the profile of the invading species in response to the presence of a species already there. So there's the same number of generations, 8 generations. It's spread much less far, and the shape has changed too, interestingly enough. And so this is a way to experimentally test that kind of idea and point that out. And what we can also do is that over the years, we have developed a very detailed model that takes into account all the different kinds of stochasticity present in the system. I don't want to go through any of the details. It would take forever. It started off with a model in a paper that Brett and I published a long time ago. And the reason we did that is our first spatial model, we couldn't get the variance right. So we went back and did this. And one of the things about this work is that it enables us to measure the variance in the outcome. So our attempt of putting in stochasticity is not just to sort of see what it does to the mean behavior, but to understand what it does to the variance of the outcome, which then is a measure of how well you can predict. So we think that is key, and the only way you can do that is to get, we typically will run somewhere on the order of 8 to 10 to 12 replicates, depending on the experiment. And that just says what I said. And this is the detailed model matching the data as well as it can. This shows you the variance is illustrated by looking at, this is the generation 8 only, which shows you how much variability. Those are the different replicates. And then this is the competition model, same generation, and the 95% prediction interval. And you can see the degree of variance that is present, which begins to think about the role of stochasticity. And then we can look, for example, at excuse me, competition with our detailed model, run it for 100 generations, and see what happens. And you get the same kind of behavior out of the detailed model that you did out of the much more general results that were in the original model. And so let me finish up by saying, essentially, to emphasize again that many applied problems require a spatial approach. It's really important to take sort of fundamental kinds of results. I know that Mark more recently has actually done much more work of an applied nature of his own that's very, very interesting. And essentially, one of the interesting challenges is to take work like the work I've mentioned here and use it to look at questions of applied interest. And we need that. And this kind of interchange is really important. And once again, happy 60th birthday to Mark. And I'm happy to stop there.